recorded. Okay, so last time we were like uh, doing extensions of probability spaces, so of not probability spaces, of measure spaces. So basically, we had a sample space which so the points of the sample space are events. So they are like thick points that can be divided. So this is like omega 1, omega 2, omega 3, etc. And we can divide them by being like more there are two reasons why we would like to divide them. First, because we want to be more precise. So, for instance, we have our sample space omega, which is the sum of two dices of two dice. But we want to consider the dice taken like on their own. So the results of sorry, I always used another notation. So um, so we can consider the results of the dice by their own. Um, so this is a bigger sample space because we are being more precise, and to the event two, only one will be the same as the event two, but the event three, which is elementary in the previous sample space, corresponds to like 1 2, but also to 2 1. So we are like dividing the elementary events into events. Now the elementary events of omega are not anymore elementary; they are events. And this new sample space, omega prime, we can divide. We are being more precise, and we are dividing those elementary events more. So this formalizes mathematically by saying that omega prime extends omega if there is a function f which associates like to each elementary event which is more precise, so omega prime in omega prime, in capital omega prime, to the event omega prime, omega in omega, uh, such that omega prime is in omega. So you see, now 3 is equal to 1, 2 to 1. So f of 1, 2 will be equal to 3, simply. Which is, so in this case, f is equal to omega prime can be, is ij, because where I is either 1, 2, 3, or 6, up until 6, and f of ij is equal to I plus j in this simple case. So does it make sense? Perfect. Why it is this is one reason, and the other reason is that we always think that there is an underlying omega prime from which the randomness arises. So the randomness is here. And we observe some partial information. This was the case of like uh, when we like observe the output of an algorithm, like we we have this f, which is we type on RStudio like sample omega 1 p for some p probabilities. And this omega prime now it is unknown to us, also this f, because it's very complicated. So we have this omega prime omega, we observe only the events here, but the randomness is here in omega prime, which is like the states, the possible, the sample space. In this case of the computer, like its transistors, its microchips. So it's really a nightmare. So this is in general, it is useful to consider like that the randomness comes from a more elementary degree, like the computers, and we observe some partial information. So the example here was so the main example of this topic is the following: when we have two experiments like and omega n and lambda 1, lambda m, we have a sample space that contains both, and it is in some sense minimal. This is not necessary, but minimal. We have this Cartesian product, which is simply the set of strings with two letters, where the first letter is in omega and the second one is in lambda, which is simply omega 1, lambda 1, omega 1, lambda 2, until omega m n lambda m. So this sample space like extends in this way omega and lambda. So we have the first coordinate, which is a function which from omega lambda it gives you omega. So and y, let's call them x1 and x2. That from gamma gives you lambda. So and it associates to the word the second letter, so lambda. Okay, so is this clear, this notation?
The notation is clear. Maybe not. It's not that easy to imagine some application for it right now. Maybe.
Okay,
Like, why should we do it? Yeah, like. Yeah.
So the reason why I'm doing this is so it is for when we will do repeated experiments. So like for instance, omega is equal to lambda, which is equal to a coin toss. So we toss twice a coin, and our gamma is equal to 0, 0, 0, 1, 1, 0, 1, 1. Now, the question is, this sample space is something like this. So this is 0, 0, 0, 1, 1, 0, 1, 1. On the x-axis, you have the first coin, 0, 1, and on the second one, on the second axis, the second coin. So I'm saying these things because I don't know, when you like do an experiment, I don't know, you want to, you want to do a psycholinguistic experiment. There are a lot of them. Like I don't know, you have two variants of the same word, one dialectical and the other one more formal. And what do you do? So let's call this dialectical zero and this formal a one. So they are like, you imagine that they are like coin tosses, and you have a whole, so you have uh, a lot of informants, so let's say AB100, AB, these are like the identifiers of the persons, of the people. And here you have a dialect, the variable which tells you if it is dialectical, if they used a dialectical or dialectal, I don't know, dialectal or formal variant. Maybe here you have also other variables, so like, I don't know, if the context of the word, of the statement, I don't know, was mm, taken from I don't know, well, you can imagine such an experiment to see, like, you have a research question, you want to see if a word is mostly used in its dialectical form or dialectal form or in its formal variant. Here you have 0, 1, 0, 0, 0, 1. You like interview five people, and so here, well, the set of possible outcomes is 0, 1 times 0, 1 5 times. Um, what I plan to do in this lecture is to first to say that if you have a probability here on this space, okay, here we are doing probability theory. So we start from a probability and we can compute everything. But actually, real life is much more difficult. We use probability theory, but we have to estimate this p and assume making some assumption on it and a lot of stuff. So now what I wanted to do is to give a probability on this bigger space, which is our goal, which we cannot, but we cannot know. So we put a probability here, and now we can compute everything. Basically, I wanted to compute the probability like that the first informant says its dialectal form. And so now the goal is to like to give a probability measure here and to compute stuff. In of course, and also my other goal was to say that if we know the probabilities for each informant, there is no unique way to, so if we know the probability that this person says a dialectal form, and we know the probability that this second person says a dialectal form, actually we have we would like to recover this big P, but we cannot. We have to make some assumptions to recover this P. So the goal of this lecture is twofold. So given a probability here on gamma, which is the product of omega and lambda, which is in the previous case, this was 0, 1, and this was 0, 1, like we are interviewing two people. Um, and this, so the first goal is we give a probability here, and we want to compute the probability on omega and on lambda separately. This is a simple computation, and we will do it now. The second one is that we start to notice that if we start from a probability here for the first person and a probability for the second person, sorry, lambda, from this is not sufficient to recover the knowledge of the complete knowledge of the experiment, which is this one. So, for instance, if omega, so for instance, let's take lambda equal to, so if omega and lambda are the same, if we are interviewing the same person, like maybe he is more likely, that person is more likely to say a dialectal form twice. So, but if we are interviewing different people, maybe these quantities are the same, but jointly the experiment has different probabilities. But now these are only words. Maybe let's be more precise later. An example of it will be like in the next second part of the lecture, where we will see this at work. So probably maybe I don't know if this made stuff clearer or okay or worse. But okay, so now let's do this. So let's set some notation. So we have our gamma, which is the Cartesian product, and we have the projections x1 and x2, um, which give me from this two-letter word the first and the second letter. Then we can, well, we can define how do we write the event e omega, which is uh, mm, omega happened. Well, this is the set of two letters word where the first one is fixed. So only the second one varies because omega happened. So it is like omega lambda 1, omega lambda n. Okay? So if we are drawing a picture, here there was omega, here there is lambda 1, lambda 2, lambda m. We are writing omega, this event, as the sum of these squares. sorry, as the union of these elementary events. This is E omega. And also F lambda is the set of, yes, no, sorry. And how can we write this event? Well, it's the event for which the first letter, sorry, is the set of words omega bar lambda in gamma, for which the first letter is precisely omega. So this is a way of writing it. So now also omega bar varies, but then here we put also the condition that omega bar is omega. It's quite, why do I do that? Because now we can write this, we use a shorthand notation. So this is actually omega bar is equal to omega. So this is quite, I mean, is the same. Okay, we use a shorthand notation and we write this event as x1 equal to omega. So does it make sense, this event? So I forget like about gamma. I'm simply writing this. So this will be very, very useful. Does it make sense? So this has to be read like the set so, of two-letter words where the first letter is omega. So this is what is written here, and this is simply a shorthand notation where we forget about this is the set of two-letter words. I only called omega bar, lambda, the generic word, and this is the condition that the first letter is omega. Omega is fixed.
So omega is fixed, but in this set we have like subsets in which every subset contains only one fixed omega.
Exactly. No, yes, exactly. If I understood correctly what you said. So the omega each let's fix omega equal to omega 1. So E omega 1 will be equal to omega 1 lambda 1 omega 1 lambda 2 until omega 1 lambda m. And this is equal to the set of omega lambdas for which omega 1 lambda, where lambda varies in lambda, in capital lambda, or the set of two words omega bar lambda, for which the first digit, the first letter omega bar lambda is equal to omega.
And then we go from this omega to fixed omega 1, or yeah, am I right?
Sorry. Yes, here there is omega 1. Yes, you're right. No, sorry. This is simply a notation. It's like, uh, so graphically maybe it's better, like we fix omega here, and we take the set of two-letter words where omega is fixed. So we take this column and we make lambda vary. The only fact is that usually here omega is fixed outside the event. Now I want to look for omega bar lambda such that omega bar is equal to omega. So I have to move this omega bar until I reach omega. So it's like the generic element is omega bar lambda, but I want to fix omega bar to be equal to omega. So like the set would be like omega bar lambda such that omega bar is equal to omega. And this is equal to x1 omega bar lambda equal to something. I mean, it's more why I'm doing this because this notation will be really useful because it does not require like knowing it's really the domain of this function x1. So it will be it simplifies a lot. Um, so does it make sense? If it makes sense, I go on. Uh, yes, okay. So this is it is more complicated now than it will be later because and in the same way like x2 equal to lambda is equal to the set uh, omega 1 lambda omega n lambda. So in particular the probability of an elementary event omega lambda is equal to the probability of x1 equal to omega and x2 equal to lambda. So we will use also this notation. Denotes this is an intersection. So we this is like is the set of two. This would actually, if one would have to be precise, should write in this way. This is the set of omega bar lambda bar in the product such that omega bar is equal to omega and lambda bar sorry, is equal to lambda, which is only the probability of omega lambda. This is equal. Okay. Uh, so here I'm also confusing sets with elements. So, but I hope that this will not be confusing because it's actually very easy because, for instance, I don't know, let's take the x1 denotes is like equal to 1 if the person, the first informant, sorry, let's take again the sample space omega of two informants, like 0, 0, 0, 1, 1, 0, 1, 1, where like the first digit corresponds to the first informant, and the second one to the second informant. Like 0 it means like the informant used a dialectal form, one a formal form. I mean, use the formal variant. And let me call this not omega but gamma because it's a product space. So in this case, x1 is simply equal to 1 if the first informant used the formal variant. Zero if the electal. So instead of looking at gamma, we rather look at this exercise and we write like x1 equal to 1, x2 equal to 0. This is a possible outcome. And this is a good notation. This means actually the probability of 1, 0. But, okay, so does it make sense? So it's another way, it's simply another way to write the same event. Um, yes, I can. Can I go on? Yeah, okay. Um, if not, I can. I mean, I can repeat it. So, okay. So now, well, we were like, um, so let's take gamma and the probability on gamma. How do we define a probability on omega? Recall that gamma is equal to omega times lambda. We need to define a probability on omega. How do we define a probability on omega? Well, this is easy because uh, let's take the event omega happened, like omega happened, which was like omega lambda 1, omega lambda m. Um, well, the probability of omega of the elementary event for omega. So omega is an element of omega. Its probability is equal to the probability. I define it to be the probability of the event omega happened, which is simply the probability of omega lambda 1, omega lambda m, and this is equal to p omega lambda 1 plus p omega lambda m. Okay, this is, does it make sense? These are the probabilities of these events, these elementary events, and the probability of omega is the sum of the so we do this operation which is called marginalising. Why it's called marginalising? Because what we are doing here is we have the event omega, which in the sample space gamma So gamma is the Cartesian product. Here we have lambda, m lambda m minus 1, lambda 1, and these squares are denoted by two indexes, omega and lambda. So omega append is simply this column, and I'm summing the probabilities of each one of these squares. So the probability of omega is simply the sum of p omega lambda 1, p omega lambda m. So I'm taking the marginal of these squares. So I'm summing all these squares. And does it make sense? Okay, this is like is not really is not really complicated because it's simply taking a sum. Then the problem is the converse. Like we want, we have now two experiments, omega, p omega, and so we know the probabilities of these experiments, lambda, p lambda. How many, is there a way to determine the probability of this experiment performed in a joint way? So this procedure is much more difficult, and it's called coupling. No, it's not much more difficult. It's simply there are not so many as much information to recover p. Why? Because for instance, to fix the cardinality of gamma is equal to n times m. The cardinality of omega is equal to n. The cardinality of lambda is equal to m. Fixing a probability means fixing uh, n minus. So is if the space has k elements, to fix a probability, you need to fix k minus 1 numbers. So in particular, we need to fix n times n minus 1 numbers. We know the probabilities on omega and on lambda, so this is what we need to fix. And we know n minus 1 and n minus 1 numbers, because we know the probabilities on omega and on lambda, so these are what we know. So we need to fix the remaining. The remaining is n times n minus 1 minus n minus 1 minus n minus 1, which is equal to n minus 1 times n minus 1. So there are a lot of, this is like the number of ways in which uh, you can choose this probability here in such a way that you can recover in such a way that the marginals are the ones which I gave. So let me be more precise by saying what are the conditions. Well, the conditions are, now we know this p omega and this p of lambda, and this has to have to be equal to p omega lambda 1 plus p omega lambda m, and p omega 1 lambda plus p omega n lambda, where lambda is in lambda and omega is in omega here. So now these are known, and these are the incognitas. Um, so, in such a way, the exercise is to fill a table where you know the sum uh, of the to fill a table with numbers A, B, C, etc., where you know that the number what numbers you have to have on the summing the columns, like P omega 1, P omega n, and P lambda 1, P lambda n. So, and when you sum the rows, there are many ways of filling them, of filling it. This is the problem. And what we did last time was like an example of it. So we toss two coins. We can toss them independently. So the coins are fair. So the probability of x1 equal to 1 is equal to 1 half. The probability of x2 equal to 1 is equal to 1 half. But what is the probability that x1 is equal to 1 and x2 is equal to 1? So this is like the prototypical question. And well, there are so many possibilities. So like we toss the coin independently. And this is like we use the total probability formula, and we first toss the first coin, and then we toss the second one, but we have to know uh, we know the result of the first one. This is always true, this formula, by the way. And the independence assumption is simply we assume that we can remove this, that this is equal to the probability that x1 is equal to 1 and the probability that x2 is equal to 1, which is 1 over 4. But maybe we are tossing like the same coin. In this case, it is not true. So maybe we are to x1 is the same coin. So we are looking twice at the same video. So like the probability that x1 is equal to 1 and x2 is equal to 1 is equal to the probability that x1 is equal to 1. Uh, so this is always true. But now, if the first coin is equal to 1, then the second, we are looking at the same coin, so this is equal to 1. So this is equal to the probability that x1 is equal to 1, which is 1 half. Or maybe we are tossing them in another way, so in such a way that if x1 is equal to 1, x2 is equal to 0. So in this case, this would be 0. So they correspond in three different probabilities, like we computed them last time. We did an exercise which consisted in finding all the probabilities. for which x2 and x1 are fair coins. So the probability is 1/2. And we found something like this. So the probability of 0, 0, so p00, p01, p, sorry, um, p01, p10, p11 was something like alpha 1/2, 0, 0, 1/2, plus 1 minus alpha 0, 1/2, 1/2, 0. So these were all the possible probabilities for which uh, the coins are fair. So there are many ways of, so let me put it into more precise way. So uh, these are all the possible probabilities on the joint state space. So let me call it gamma, since we call it gamma. For which P, the probability is x1, so x1 that goes from gamma to 0, 1, and x2 gamma to 0, 1, the first coin, and the second coin are fair coin. So if we only look at the first one, are fair coin. Probability that x1 is equal to 1, which is equal to p1, is equal to p, sorry, is equal to 1/2, and the probability that x2 is equal to 1 is equal to p, which is equal to 1/2. Um, and okay, so there are many ways of considering jointly many experiments. So let me check what time is it. Okay, I can go on for a while. So, uh, okay, we can do it in general. So, in general, by looking at which kind of information do we need. But, well, this is actually quite easy because what the further information we need to have to define. So, we know to define a probability on gamma. What do we do? Well, we simply use this formula here, P, so P of omega, let me write it in this way, P omega lambda is equal to the probability of omega and lambda. Sorry, omega, sorry. omega lambda, which is equal to the probability that x1 is equal to omega and x2 is equal to lambda. Well, this is equal to the probability that x1 is equal to omega. And then, so we perform first the first experiment, like we toss the first coin, we ask to the first informant. Then we ask to the second informant, or we toss the second coin, but we know the result of the first informant. So this may change drastically this probability. So what do we need to know? Well, this is equal to P of omega that we know is the probability of the first experiment. But we need to know the probabilities on the second experiment given the first one. So we need to know these numbers here, which we define to be P omega, sorry, y eta lambda. Lambda given omega. So we need to know, so definition, or maybe notation, P of lambda given omega is equal to the probability of that the second digit is lambda, given that the first one is omega. So once we know this one, so and this, how many numbers are there? Well, omega varies in omega, which has n elements. Lambda varies in lambda. So there are many of them. There are like n times n, plus some, minus some, like actually there are n minus 1 times n minus. So, I'm not interested in being precise in this computation, but there are like, for each omega, there is a probability. So there are like the order of numbers here is like n times m, which are those that we need. Like we needed some more information, but okay, so to define a probability on the product space, we need to define p omega lambda. So it's not so p omega lambda is equal to p, the probability that the first experiment gives me omega times the probability that the second gives me lambda given omega. So this is the magic formula. And we know these ones, but this one can be very, we don't know them, all of them. Um, yes, we know something about them. We know that the probability of lambda is equal to the sum of the probability of lambdas given omega times omega. This is the total probability formula. So there is some relation between them. But in general, apart from these relations, we know nothing. For instance, and then I go to the Bernoulli trials and to do some more linguistic stuff. So, for instance, mm, the coin tosses, the probability that x2 is equal to 1, given that x1 is equal to 1, can be equal to uh, the probability that x2 is equal to 1 if independence is assumed. 0 if we toss them bounded in some way, or it can be 1 if x2 and x1 are the same coin. So there are many possible choices. And in general, so here we can let me finish with a remark. So in the independence hypothesis, reads here that the probability of lambda given omega is equal to the probability of lambda, which we know. Uh, so for every omega in omega. So in this way, the probability of omega lambda, this is equal to the probability of omega times the probability of lambda given omega, which is equal to the probability of omega times the probability of lambda. So if independence is assumed, is assumed from the probability of each single experiment, I can recover the joint probability, the coupling between the two probabilities. But in general, it's not true. So is the reason why when you do an experiment, like you don't want to have, like, I don't know, you are conducting a poll, like you want to call people to see for whom they will vote. So mm, you will not call, like if you have like money only to call 20 people, you will not call them all of them in one region. You will try to be as independent, as most independent as you want, because I don't know, if you call a person from the same family, they will not, their opinions will not, I mean, will not be, there is more chance that they will vote, I don't know, they will influence each other. And usually models, when they assume independence from, uh, like in the polling example, like for instance, this makes sense in the linguistic example, like you have a dialectal form and a formal form variant. If you call the first informant, maybe is this one. So you would and like asking which form they will use to the to the first informant is one experiment. So this is like omega, and this is like lambda, which possible answers 0, 1. Like if you ask, uh, if you repeat this experiment, so with this informant and this one, this other informant, you may model like this experiment as if they were independent. So the probability that x1 is equal to 0 and x2 is equal to 1 is equal to the probability of x1 equal to 0 times the probability of x2 equal to 1. Um, but this is I mean, it's not a guaranteed. It's not you wish this because in this way you know because because non-independence is difficult to quantify. So you wouldn't be able to you would have much more parameters to choose. But in order to that this assumption to be at least approximately true, you cannot choose the informants from the same family because they will speak probably they will tell you the same form. So probably it could be that uh, this has probability zero because they speak in the exact way. So um, if you want to, in this case, this hypothesis would be false. So when you try to do some statistical analysis that assumes independence, you really need to ensure that rows are independent, and this may be a problem. But this will be for the next semester. Now we only have to define, we assume that this is true and we compute stuff. In particular, we can do Bernoulli trials. So Bernoulli trials is the same stuff, but with many coin tosses. So apart from, so I speak about coin tosses, but I hope that you like understood that maybe they can model other stuff. So is it clear that like they can model an experiment like when you ask a yes/no question? So they are not coin tosses, but x1, xn, etc. coin tosses. Uh, independent coin tosses, so which tossed independently uh, with parameter p. So let me be more precise. So the hypothesis of identically distributed, so they are identically distributed uh, means that the probability with the parameter p, which is a number between 0 and 1, means that for each I, the probability that xi is equal to 1 is equal to p. Independent means that if we do this, uh, if we want to compute the joint probability, so we want to compute the probability, for instance, that x1, yes, okay, xi is the ith contos, so it's equal to 1 if the ith contos is gives head, 0 otherwise. So the probability that x1 is equal to little x1. So let me take little x1, little xn to be equal to be either 0 or 1. So for instance, they could be like x1 equal to 0, xn equal to 1, whatever numbers. They are this. So this is a way to be more generic. Um, so this probability. So do you understand what this probability mean? Yeah, no, no. Okay. Yeah, I think maybe. So maybe let me be more precise because otherwise it's. So here omega is the set of infinite strings x1, xn, where xi is in 0, 1. For instance, 1, 1, 0, 1, 0, 0, 1, whatever string is an element of omega. Xi is simply the ith digit. Okay. Now I want to see what is the probability that xi is equal to little xi is equal to p if xi is equal to 1. 1 minus p if xi is equal to 0. Why? Because if xi is equal to 1, we are computing this one. And this is equal to p. If xi is equal to 0, we are computing this one, which is equal to 1 minus p. So we can compute the probability, we fix some numbers x1, xn in 0, 1. For instance, if n is equal to 3, we could choose x1 equal to 1, x2 equal to 2, x3 equal to, sorry, x2 equal to 1, x3 equal to 0. And we can compute the probability that the first digit is 1, the second one is 1, and the third one is 0. Um, this is equal to the probability that this is something that we can compute. This is like the set of strings is the probability that of the set of strings which start with 1, 1, 0, and then go on with whatever results. Um, so precisely to avoid writing this, I introduced this notation. and also because it is very useful to forget about the space from which the randomness comes from. But in this way, we can write like first we toss the first coin, then we toss the second coin, but we have to keep in mind the result of the first one. And then we toss the third coin, but we have to keep in mind the result of the first and the second one. You can check that this is an equality simply by is the definition of conditional probability. And now we use the hypothesis of independence. The hypothesis of independence means that we can, if we toss the third coin and we know the first two results, to us is really, it doesn't tell to us anything. So this is the equality. And now, well, we know these probabilities because we know the probabilities that this is P, and this is 1 minus P. So this is equal to P squared times 1 minus P. So in general, the hypothesis of independence plus the distribution of each single x allows us to compute this kind of probabilities. Now, what I was writing before was the generalization by taking, since I don't want to, I want to take into account every possibility. Instead of writing 1, 1, 0, I will write here x1, x2, x3, and say that x1, x2, x3 can in particular be 1, 1, 0. So that is it was what I was doing before. So now in the general case, we want to compute probabilities of this form that the first coin toss gives me x1. x1 is a number, it can be either 0 or 1. x2 is equal to x2, and x2 can be either 0 or 1 until n can be whatever, which is equal to xn. xn also is in 0 or 1, and we do the same stuff. So we toss the first coin, then the second coin, but we need to recall the result of the first coin toss. Okay, let me do also the third coin, but we need to remember the other results. Etc. Times until we arrive to the last coin, but we need to remember all the other results. So we can compute the now with the hypothesis of independence. This is true for every sequence. I mean, for every P. It's a matter of definition of conditional probability. Now we use the independence hypothesis. And we say that we can neglect these conditioning events. And we obtain this probability. Now, we can compute them, these things, because we now use that they are equally distributed, with probability P. So, in order to do that, we need a smarter notation. But let me first say that here we have P. How many P's do we have? Well, we have P if this is 1, 1 minus P if this is 0. So actually what we will have is P, okay, sorry. We have P if this is 1, 0 otherwise, 1 minus P otherwise. So we'll have P a number of times, which is like how many ones do we have? So P times the number of ones. So, but what is the number of ones in x1, x2? Is the sum of xi. So it is, the result will be P to the power x1 plus xn times 1 minus P to the power n minus x1 plus xn. Why? Because if xi is equal to 0, here I'm not adding anything. And here I'm adding a 1 minus p. Vice versa, if xi is equal to 1, here I'm adding 1p. But here I'm not adding anything because I'm adding 0. 1 minus p to the power of 0 is 1. So I'm not adding anything. But how to see it more precisely? More precisely, well, the probability of xi equal to xi, this is equal to p if xi is equal to 1. 1 minus p otherwise if xi is equal to 0. Well, let's look at this expression. P to the power 1 minus p, p to the power xi times 1 minus p to the power 1 minus xi. So this is equal to p if xi is equal to 1 and 1 minus p if xi is equal to 0. So basically, p of xi equal to xi is equal to p to the power xi times 1 minus p to the power xi, 1 minus xi, if xi is in 0, 1. As simple as that. So we can compute the Bernoulli trials, the probability of the first n tosses, simply by writing this equality here. Here is the independence. Sorry, I have written exactly the same stuff. So here is the independence hypothesis. And then here is the equal distribution of each coin. So p to the power x1 times 1 minus p to the power x1, 1 minus x1 times p to the power x2 times 1 minus p to the power 1 minus x2, etc., until p to the xn times 1 minus p to the power 1 minus xn. And this is equal to uh, 2p to the power x1 plus xn times 1 minus p, we sum n times 1, so n minus x1 plus xn. So this is the probability of each single sequence. But it's important to know where the independence hypothesis enters. Uh, so does it make sense? Okay. Then the next part of the lecture, we will see a linguistic example, which is more interesting. But this is like it's important to know uh, where the independence hypothesis enters, because actually it's also when you do stuff more intricate stuff like law of large numbers or central limit theorem, it's very important to have this property here. So maybe let's take a break. So 20 minutes break if you want, and then we will see at 6. Sorry. Okay. Uh, Sorry, no, at 6 here.
At eight, at
Okay.
8 for us, at 6 for you.
Thank you. See you. Uh, Now we will do like more interesting, I guess, at least more practical stuff in this part of the lecture. So we will work on with R, and we will like explore this data set, which is called Dracor. I don't know if you know it. It is Dracor because Dracor stands for Drama Corpus, and there is a specific package, AirDracor, which was designed by Ivan Pos. One of the, I guess, one of the designer was Ivan Pozniakov, which was previously a professor teach the course of statistics here, together with Ilya Shurov. And this package helps you to visualize and getting data from this corpus. So let's see. There is also the Russian corpus, but I don't have the Russian keyboard. So let's go with the German corpus. So let's call this variable. Let's download the data. So uh, the function is get Dracor, and the corpus is German, the German one, which is is this one. So let's download it. And also let's visualize it. So it is not trivial to when you have a huge amount of data how to visualize it. There are some R tools that help you. One is you can is from the package scheme R and the function scheme, which helps you to visualize a data frame. In this case, okay, it has downloaded. So let's look at it. So, okay, it's really slow, this computer. I don't know why. But okay, what does the scheme function do is it takes you all the columns of this data frame Okay, let me also plot the first values. So the rows of this data frame are different. So this is the output uh, of plotting the head of the data frame. So there are many plays, and the data frame has also different columns. So each row consists on a different play. There is the play name, the year in which it has been it has been first, I guess, displayed. Then there is the title, okay, the subtitle, and other different data. And you can look at the columns by this function scheme. So there are like different columns, 21 which have character variables, one which has a variable that is a list, then 34 numeric variables, and 5 logical variables. And you can look at some statistic, so like um, if the columns are complete, if there are some missing data, and different kind of data. Now we will not really dig into more sophisticated values because there are like also some graph defined like if you go to the web page actually of the drama corpus, you can see a lot of different stuff. We will simply choose one play and download the text. And so let's first download to download one text. We can use the function from AirDragor. The function is get, I guess, text, yes, text in a character form. So, and here we have to pass the name of the text we want to download. I don't know if you have your favorite drama in German, but I don't. Maybe I'm not really good at literature, but let's download Brecht. So just simply let's see if they have it. So let's look at let's select from this uh, data frame. Let's select or filter the rows for which the first author, which is a column, is equal to Brecht. Let's see. I don't know German, so maybe probably it's written in a bad way. So let me see if it works. No. Okay. Well, let's simply. Okay, you can also view this data frame. Ah, okay. Probably I saved it in not. Okay. How did I call this? Yes, I. Ah, okay. So if you do view a data frame, it plots the whole data frame. And here we can look at, I don't know, we can order it, we can do the usual stuff. There are some different comedies. I don't know, I don't know, okay.
Maybe let's be boring and just choose Goethe.
Okay, let's be
There was
classical.
Goethe. I've seen it in the head. Yeah, in the first 10 rows.
Let's, probably there is, okay, ecco. Okay, perfect. So let's download this Gother Elden Wieland. Okay, so we go here, we substitute uh, in what we have written before, like the AirDracor function get text character spoken, and we put here the name of the drama, and we save it in as get. So we also put the um, there is another variable which makes you download as a one string of characters. So let me recall because I forgot. So I go here to the helper and I write get text uh, character spoken. So split text equal to false makes a huge string, gives you the text in a huge string format. So split the text equal false. And okay, what happened? I have to pass also the corpus. The corpus is the German one. Okay, now let's see what, let's plot this variable. Let's first check which class is. Uh, it's a one character, so a huge, all the play went here. So let's also view it simply because why not? Uh, why did I put the commas? Sorry, it's still one character, but okay. View. Okay. So yes, a huge. Now, okay, maybe it's not the best way to plot it with view, but we can simply write get, sorry, yes, and okay, it gives you all the play. So, what do we want to do with this? Um, we so one of the first articles, there is this famous theorem which is called the central limit theorem, which we will do in the next, we will have to do in the next semester. But the fact is that it holds for like Bernoulli, the Bernoulli trial. So if in really in an easy term, so if we sum all the elements of the so no, this is the law of large. Okay, it doesn't matter what it is, but the most examples of 0-1 sequences do not follow the Bernoullian the Bernoulli trial distribution that we defined before, which was the one that is because there is no independence. So what I want to do here is to transform the consonants into ones and the vowels into zero. So and to check that the distribution of one and zeros is not the one you would expect if they were independent. So, of course, vowels and consonants are not independent because you will we will see I will ask you later why not, but it's kind of evident. But however, the dependence is not so. Let's try to do it and then first. So. Um, okay, so let's do some preprocessing. Let's simply transform this data into something we can handle. So, into what we want to do. So, by the way, one of the first articles, sorry, the founder of Markov chains, which are now like the most widely used topic in mathematics, like the first example he made with something that was not independent, like consonants and vowels. So where the hypothesis of independence fails was about an example like this, but using the Eugen origin. So basically, Markov what did was taking pencil and paper and counting the number of vowels and consonants in the way we will do it now. So I basically have read the paper and am reproducing like his study, part of it because uh, okay. So let's do so we can use this function g sub to substitute patterns with other patterns. So I want to eliminate this slash n that simply mean that the line breaks. So they are not there because they are in the place. So like let's remove these patterns from and substitute with nothing. So simply to eliminate those slash of n in the data German no God, sorry. And let's see what do we obtain. Uh, you obtain exactly the same text but without the slash ends. So, and let's save it into,
Probably it's better to substitute it for a space because otherwise we have dot followed by the letter without anything between them.
exactly, yes, that's good. I will do it. Okay, sorry. So I save this into the variable go1, let's say, and follow by removing the spaces. And how do I do? Simply uh, I substitute the vowels. No, what is not a vowel? So a b I u. So uh, this selects only the vowels. So it's a character which is a vowel. I don't know how to write this u with 2 points. Then I will not do that. But and now I put this symbol here that tells me that what I'm selecting is exactly not what I'm writing here. So I'm selecting everything apart from the vowels. Um, so probably it is better to uh, first select the vowels and put at zero. Ah, no, okay, no, I select the consonants, sorry. Ah, no, okay, no, I simply remove the spaces. You were right. With the I remove the spaces with and I place no. So you were right. You were right. And this gives me. Okay, I didn't save the variable. Okay, now I I remove the. Here I'm choosing whatever letter and ah no, okay, no, no, I'm sorry. Here I should let me see. Yes, I have done the converse. So let me put here a complementary. So now it should be better. Okay. Of course, German has more letters, but I don't know actually how to write them. Hope it will not affect too much what we will do. So now I can place a one instead. Sorry. Uh, Instead of the vowels. Sorry, a one instead of the consonants. So and let's save it into got three, and then I place a zero instead of the consonants. So I substitute what is not a one with a zero, and then I use this. Okay, let's see did I get. Um, Okay, now this is nice, the result we obtained, but they are still saved in the computer, not as a sequence of zero and ones, but as a character, so it cannot do the operations we want to do with them. So we have to First, to separate it, so let's call this function. So from this package that allows you to treat strings, let's uh, split the string. So string split, if I remember correctly. Yes, and let's pass this got for, and let's split at every point, so every letter, and and we want that our output will be in a vector format, so simplify equal to true. Otherwise, it will be a list. And let's save it into got 5 because we still have another passage. So what's the other passage? The other passage is mm, what happened? Mm, it's only my computer that is slow probably, and probably get that writes too much. So uh, yeah, can they? I don't know what. Why it's no, there is something wrong. Um
I don't mind striping only the first 100 characters just for the ease of computation. Maybe it'll make
yes, but
things
but it's
faster.
not a question of fastness, I guess, because the output is simply bad. So probably first the string, then the pattern, then ooh, okay. Here it was right. This output, it was an output of zeros and ones. Yes. Then I want to split them in different string split. Okay, I split simplify equal true. What's wrong with that? Okay, I will try again to run it, but I mean it will not change the output. Okay, probably let me try. Yes, let me try with a smaller. Uh, so let me define like a equal to no 10011 this one, and let's use string split with this a here. Split it. Okay, let's try to use it. Okay, now it works. And if I try to simplify it, let's okay. And if I try to okay, probably in this way it should work. No, in this way. Okay, for some I have another version of R because before I was in another computer. So in this computer, in this version, I should like it gives me back a matrix. So I should put here the first row. So now it should go. It should work. Okay. I mean this was only technical. Sorry. Now I have this huge vector of characters. Now I want to transform these ones into new numbers. Now they are only a string which with values one. So usually in R is done uh, with this as point and the class you want uh, to transform your variable. So we want to transform this vector into a vector which has numerical values. And we need to pass here uh, the fifth version of God that we had, and we will call it God 01, let's say. Let's see. Invalid numeric, sorry. Okay, now this is the format that we can handle. So let's look. Okay, and now we can say, do they look like Bernoulli trials? So independent, and so assume that I gave you this string. So first of all, what is your guess about the P? So if they were Bernoulli trials, so the question are two. So if they were Bernoulli trials, what P would be? What would be P?
Uh, One half. Well, as we're doing something with something natural, then it would be like 0.49 for one and 0.51 for zero, say, but um, technically one above two.
No, actually, no. Why? I mean, you mean because there are more basic? I mean, I don't know how. Actually, I don't know. Maybe linguistically you are right, but I don't know. And if I don't know, I usually check the data because maybe there are consonants are more present in words. So I mean, these are this one. So my guess would be like, okay, let's take this data here and let's look at the number of ones and at the number of zeros. So let's try to do it. So let's try to estimate p. So we need simply to sum these vectors. So this gives me the number of ones, and we divide by the total number of digits. So let's see. So there are more consonants in words than vowels. At least, yes. I mean, if they were uh, Bernoulli variables, so independent, and I would uh, I would say that the parameter p is this one because now if you um, because why they should be fair? I mean, consonants and vowels are different. Here, one and zeros are not. There is no the symmetry. So and the simplest way to estimate it is to take the number of ones and dividing by the total number of elements. So if the next one is distributed according like the previous one, it's like if you toss a coin many times, it gives you half of the time zero and half of the times one. But that is because the coin is fair. if the coin is are consonants, they are not anymore fair. I don't know if does it make sense. Okay, so this is like let's save it into our estimate of p. So now, okay, there is a actually so the second question is why they don't look like Bernoulli trials. Uh, then, if they were Bernoulli trials, uh, we could the estimate they would be distributed according to Bernoulli with parameter p with parameter p estimate approximately. So we can try uh, to plot a sequence like of Bernoulli trials. We can do it with this command. So we sample the same amount of elements that get 0, 1 has, so the same poem, with so this is the size, not sorry, not sample, but R binom of parameters size, so n equal to the length, size equal to 1, and prob equal to p estimate. This are simply Bernoulli trials of parameter p estimate. And okay, mm, this we could do that and look at the difference, but there is actually a so first of all, let me again view this. So, do you have an intuition on why this is not a random sequence of coin tosses between one and zeros? So, like looking at the numbers. I mean, it's not easy. It's simply if you.
Maybe because sometimes we have kind of patterns.
Yes, that's a reason. Which kind of patterns?
See, I can spot sometimes two ones followed by zero.
Yeah, I
Sometimes,
mean, this is a good intuition. I mean, because there are many, yes, too much of this kind of things because, I mean, consonants are vowels, they are not independent. So, like, we see too much of 1 1 zeros, too much of 1 zeros, and too few, like, of a sequence. I mean, how many elements are here? There are like 15,000, and there will be not so much one. I mean, there will not be like six ones in a row. Maybe here, yes, because probably because we have removed that vowels that in German have the two dots. We are not considering them, so probably here there would be like a zero in the middle. So we will not see too much ones in a row because we cannot see like too many consonants. It will be not not intelligible. It will not be. We could not utter that word. So probably. So let me plot these Bernoulli trials and see that. Okay, already here we see like these patterns of ones. So there are a lot of it's like okay, this will never be a word. I mean, with all these consonants. So there are too much in our one and zeros. There are too little, much more change of between vowels and consonants, and less all consonants in a row. But how can we see this rigorously? Well, first of all, let me say that there is a nice way to obtain without the need of sampling with this sample command, with this Herminomian command, this variable, which I now saved in new sample, there is a nice way to obtain Bernoulli trials from this data. Do you have a way to obtain like from a pattern something which is independent? Like how can we do? Like uh, so the problem here is that two near components are not independent because if one is consonant, a consonant, then most likely you will find a vowel. So a way to, with this same kind of one and zeros, to obtain independent trials. I mean, we could reshuffle the text. So we could take the text and mix the letters. So and we can do it from here. So we can take this variable, uh, go this text, and reshuffle it. This samples reshuffles it. So and now if okay, what do we do with this? So um, we shuffle the number, the letters. We obtain, what do we obtain? This is rigorous. We obtain Bernoulli trials that conditioned to have the same amount, the amount of the same amount of ones of consonants and zero. So basically, and this condition is very weak. So basically, if we reshuffle the test, we are doing the same stuff as doing this new sample because we lose every information uh, about the patterns. So let's define it. Now we have three variables, one which is the text, the other one which is the reshuffled text, and the last one which is the Bernoulli trials, sample from the Bernoulli trials. And as you said, we have used the information of the number of the single letters. Now we should use the information on the patterns, or like on two consecutive or three consecutive letters. So let's try to do it. So let's build a function that counts patterns. So let's count the patterns. Um, so we give in input a vector x, and it counts the number of and a pattern also. So a pattern will be a vector. A vector like I don't know, zero, like 0 and 1. The output of the function will count the number of 0 ones in the string. So we define this y as the logical vector which tells you, okay, for I that goes from 2 to the length of x, um, y of I is equal to the logical vector that tells you, gives you true if x of I minus 1 is equal to 0, and if x of I is equal to, sorry, not to 0, to pattern, we would like to change the pattern also. So to pattern 0, let's say 1, and to pattern 2, So let's take only patterns with two elements. And this gives you true if the I at the ith place there is that pattern. False otherwise. So yes, let me also initialize it, because uh, it's not strictly necessary, but sorry. So the length of this vector y is the same as the length of x minus 1, because if we take two elements, there will be one. If we are checking for the patterns, we will have to stop at not at the end of the vector, but the place before of the vector x. So this vector x y goes from has the same length of x minus 1, and it tells you if the pattern is there or not. So it should work, this function. Let's see. Incredibly, it works. And let's count the patterns of, of vowels and consonant that we find. So count patterns. Um, let's start with our true text. Got 0, 1, and the pattern is 0, 1, let's say. And let's see if it makes sense. Object X not found. Okay, this was a small X. Okay, perfect. Okay. I have to return something, of course. I will return uh, the number of truths. So a true is a one. So if we sum y along y across y, we will get like true equal it's equal to one when we sum it. So it gives us uh, it sums one if the pattern is there, if it's zero if it is not there. So this sum gives me the pattern, the number of patterns, and this zero, which is not true. So let me see what is wrong. Got zero one. Probably I should put here a parenthesis. Let's hope it was this one. Uh, pattern one, pattern two. No, not logical. Ah, ah. Okay. I had put here not um, a this double equality checks if they are equal. If you put here only an equality, uh, simply tells you that xi has to be equal to assigns to the variable xi this other element here. If I put here equal equal is a question. It's like is xi equal to the second element of pattern, and it gives you true or false whether this is true or false. Now I've counted the patterns. Now let's count them. So what do we expect if we are doing it on Bernoulli trials?
We'll have
So
less of those patterns, many, many less.
exactly. So how was it called? The new sample. These are for sure Bernoulli trials. Uh, okay, and let's check also that the shuffled ones are similar. So the shuffled text 01, and we have also omitted some. So this makes sense. This makes sense. So the text that we have reshuffled works as a Bernoulli trial, while our our text, I mean, this statistic seems really far away from the one we would expect. So in probability there are no proofs because maybe it was a Bernoulli trial, and we are in the very unlikely event in which we go. So this pattern doesn't have probability zero, but it is so small. I mean, okay, we will do it rigorously next time. Not next time, sorry, the next semester. But it is not easy to understand rigorously. It is called hypothesis testing, and it's not really. One has to think about it. because this string here, the one that got wrote, has the same probability of happening than this probability, this string here, new sample. Um, because if you go, they have the same number of p's and 1 minus p, and so the same number of ones means the same probability of happening. So it is not clear. One has to define a statistic like this one and check and define what is unlikely. So it has to define. It is not. I mean, it is not trivial, but in any case, it could. In any case, whatever your definition of unlikely, this could happen. But it is so unlikely that uh, most likely it is easier to think that God wrote a text and not I mean, didn't choose the vowels and the consonants in such a way, in an independent way. So, but this is obvious here, but in other cases it might not be. So let's also check one other stuff. Um, what is that I wanted to check? Well, that okay, so yes, actually I was curious about uh, if we take Markov didn't have like the opportunity of reshuffling it, so because it didn't have a generator of random numbers. So what Markov did actually was, okay, I won't consider like I will reshuffle it in this way. So I will take the first number and associate it with the like the sixth number, this one. In this way, like if you take the numbers far apart, you expect that they are more independent. So if instead of comparing the like the neighbors, you compare like letters that are very far apart, you expect these quantities to become independent, to become more likely, more like Bernoulli trial. So let's try to do that. Let's try to not compare the nearest to look for patterns which are very distant one from another. So let's take here instead of a minus 1, a minus 10. So if there is a vowel 10 places before, then let's see if this um, and if there is a consonant in the place I and a vowel 10 places before, this function now gives me back a 1. And then sums along each one of these. So does it make sense? Okay, so let's try to do that. So now I should define this vector. I should start from the tenth element, summing, and let's see uh, if now the result should be like more like a Bernoulli trial. So the placement has length 0. Um, why?
R starts with 1, so it's 11 that we should start probably, because otherwise it's 10 minus 10 index 0, but there is no 0 index in R.
Thank you,
That's
thank
the
you.
reason.
Perfect, perfect. And you see, now it's, I mean, I mean, when things work, I'm always really happy because you see, now, if we take very distant letters, they work as independent, as Bernoulli trials, because at least for this kind of, so if we were like to reshuffle everything in such a way that the neighbors are far apart letters, we should find it is not clear what are the patterns. So I mean, um, but at least we can say that we have no hint to believe that far apart letters they have some, I don't know, they are more independent. At least the hypothesis of independence is more likely to be true in this if we take distant letters. But of course, it is not that two letters have to be independent. It's the whole vector. So we are only saying that two far away pairs behave as if they were independent, but the whole distribution is not the one of Bernoulli trials. So, but in particular, these patterns are not influenced uh, by the fact that we are looking at vowels and at consonants. So, um, okay, this is, but okay, do you get why now these numbers are more similar? Yeah, I mean, if not, uh, I mean, you can send me emails to ask me whatever you want. But okay, now the time has ended, and so I mean, I wanted to arrive at this point, so I'm happy about that. I will try to find some exercises to give you for the next week, and have a nice weekend. Uh, so goodbye.
Goodbye. Thank you.
Bye. Thank you. It was fun.
Thanks.